So the first thing we're doing is LCA, and then it'll be segment trees, and then heavy light decomposition. Okay, cool. That is working. That's great. Alright, so let's start with the first thing, which is least common ancestor. So basically what that is let's just say we have a node here and this node here, right? The least common ancestor is a node that is higher than both of those two nodes, or I guess one of those two nodes, uh, such that they connect. So if we go from here, we just go upwards. And we go from here and we go upwards, right? The first node they connect is here. So that node is the least common ancestor. Okay, I think, alright, I'm just gonna number the nodes real quick, just so that when I refer to a node, everyone's talking about the same one and no one gets confused. Okay. Alright, cool. So let's go back to nodes 4 and 6. Right, the least common ancestor is 2, because if you keep going upward, that's the first node that they intersect with. Now, why is the least common ancestor important? So let's just say you have a path. You're just trying to look at the path from 2 to 4, right? If you're looking at the path from 4 to 6. If you're looking at the path from 4 to 6, this is a very complicated path because you have to go up and then down the tree. However, we can split the path. We can split a path from A to B into, that's an ugly A to LCA of A and B, and then LCA of A and B to B. So we can split the path from 4 to 6 into two segments, from 4 to 2 and 2 to 6, and then that's a lot easier to compute. So the first question we're going to be solving is, how do we figure out the LCA? Okay, so to figure out the LCA, right, we need to be able basically to keep going up the tree over and over. So the first thing we're going to do is we're going to calculate the depth of every node. And I'll explain why in a minute, but let's just put this node as 1, and these as 2, and then 3. And we can calculate the depth by doing a DFS, and the depth of every node is the depth of the parent plus 1. Okay, so now, if we're considering nodes 6 and 4, right? We know that the depth of node 4 is 4, and the depth of node 6 is 3. So the depth is 1 more in node 4. Okay, this means that, like, for the answer, the depth has to be less than or equal to 3, because the LCA cannot be smaller than the depth of this node here. So the first thing we do is we move 4 up, keep going up the tree until we get to a depth of 3. Okay, so now we have two nodes. Now we're looking at node 3 and node 6, and they both have the same depth. And then we simply keep going to the parent over and over again until we find one node that they have in common, which is node 2. And then that's the LCA. Now, the issue with this is that if you keep moving up the tree one node at a time, then the runtime is O of n to find the LCA, and that's too slow. We're trying to get a runtime of log n. So we're going to store this array, have this array, and we're going to use binary lifting to do this. So we're going to have an array, call it Ancestor. I'm just going to abbreviate Ancestor. It's going to be n by log n. So for example, this may be something like 100,000 by log n, I think, is approximately 20. Okay, so what this is going to represent is the parent of 2 to the power of something. And 2 to the power of whatever this j value here is. And I'll explain what that means in a second. So let's call this ancestor ij, just so that it's very clear what we're talking about. Oh yeah, and as always, if you have any questions in the middle, just continue asking, and I will answer the question basically whenever I see it, which is, I mean, there might be like 40 seconds to a minute lag, so it might take a little while, but that's fine. Just ask the question and I'll answer it when I find it, when I see it. Okay, so we're considering ancestor ij. So ancestor, yeah, let me just actually move this down here. Okay, this represents the node that is 2 to the power j nodes above I. Okay, the node that is 2 to the power j nodes above I, right? So let's just say, let me explain what I mean here using this tree. So let's just say that I is 11 here. Okay, now we're looking at ancestor 11, 0. That is the node that is 2 to the power of 0 equals 1 node above 11. So ancestor I0 would be this node here, which is 1 node above it. Then, let's just assume that there's like another node above 1. Let's call it 0, which is the ancestor of 1, and we'll give it a depth of 0, just so I can explain this ancestor concept a little better. Right? So this is when j equals 0, it's 3. Now, ancestor I1, yeah, 17 works. That's true. I mean, 20 is just a round number, but yeah, 17 would also work. Okay. Ancestor I1 is a node that is 2 to the power 1, is 2 nodes above I. So what's 2 nodes above 11? That's 7. So that is when j equals 1. Okay, ancestor I2 is a node that is 2 to the power 2, 4 nodes above I. 4 nodes above is 0. So notice how we completely skipped 1, right? We never do 1. And right now you're only skipping 1 node. But in reality, 2 to the j is 1 node above, then 2, then 4, then 8, then 16, then 32, etc., right? So this means that what this means is that we don't store the majority of the nodes that are our ancestors. Okay, so I'll first go into how to create this ancestor array, and then I'll show you how to use it to find the LCA. Alright, so the key thing to note is that ancestor I0 is simply the parent of I, right? Because when j equals 0, it's just 1 node above, and that's your parent. And then, so we're going to loop in the order of j. So we say for j equals 1 to 20, and then for I equals 1 to n. Okay, so then, actually I don't need that one. We can keep a definition on the page. Then we say ancestor ij. Okay, now let's think about this. Let's just assume that currently we have j equals 2, so we're trying to find the 4th node, right? So we have all the previous j filled out. We have all of these for all the nodes. So the node that is 4 nodes from our current node, like if our current node is 11 here, where is it? 11 here, and the node that is 4 nodes above that, which is 0, right? Going 4 nodes is the same as going 2 nodes to the 7 here, and then from 7 we go 2 more when we get to 0. So we know what is 2 nodes after us. What's 2 nodes after us is ancestor I j minus 1. right? And then we want to know what is 2 nodes after this. And that is Ancestor. So, okay, we take 2 nodes after ourselves, and then we go 2 more nodes. Okay, so this is we move 2 nodes. So we go from, in this example, we go from 11 to 7. And then from 7, we move 2 more nodes. So we go to 0. And this is how we set the ancestor array. And if you are confused, of course, ask questions, and I'll see them when the flag's over, of course. What does that number mean? That might just be the memory or something, I'm assuming. I mean, 20 million is not that bad memory. If that is the memory, or it could be the runtime. Or it could be both, actually. Okay, this is how we set the ancestor array. Now we have to use the ancestor array to find our LCA. Okay, and I'm going to erase this extra node we have here, just because we don't need that. Okay, so now we're trying to find the LCA between node 4 and node 6. Okay, so the first thing we figure out is that we figure out that node 4 is 1 depth lower than node 3. So we need to move 4 up 1 unit. Now here it's just 1 unit, so we can just take the parent, of course. But in the future, it may be like 20 units, or maybe 175, right? It may be any random number of units. So what we can do is, let's just say that we have to move up 13 units. Okay, so we have to move up 13. We can split 13 into a sum of the powers of 2. So 13 equals 8 plus 4 plus 1. So we can start at our current location. We can move up 8 using the ancestor array, and then again with 4 and again with 1. And this code will look something like this. So we have our, let's call our location at, right? That's our current location. But let's call it our starting point. Okay, so then we can loop for I equals 0 to 20. And we say, we want to know if that current value, like for example, 2 isn't there. So we don't want to move up 2. We want to know if that current value is in our value, 13. So let's actually call 13. Let's call this variable k. K is how much we have to move up. Okay, so if k and 1 left shift I, this checks if that bit is on. What the binary method seems useful. I only know the sparse table method, and it took me quite a time to learn. What is a sparse table? Yeah, okay. I haven't really looked at the sparse tables in detail, but from what I have looked at, it seems that sparse tables and binary lifting, or binary lifting uses a sparse table. You can of course correct me if I'm wrong, but that was just my notation. If I'm wrong, please let me know. But yeah. Okay, cool. So if the current bit is on, then we say at equals ancestor at I, which basically means we move up 2 to the I locations. And this will end up at the right location. So this will get us to, basically it'll get us here from 4 to 3. So now the depth is equal. Cool. So now we got our locations at 3 and 6. And we want to figure out the LCA of those, which is 2. So this one is a slightly easier technique to do so. Again, using the table that we've already created. What we can do is we can keep on moving up until if we move up, they will intersect. So I'm just going to write the code to do so, and then I will explain it. So here we're going to loop backwards from 20 to 0. Okay. We say, oh yeah, also let's call our two nodes A and B. Okay, if ancestor AK equals ancestor BK. Now here's what this means. Right, let's just say K is 2 or something. So then ancestor AK could be 1 up here. Now it could be the right answer, but our goal is to get to a spot where you're 1 below the right answer. Now of course in this case we're already there, but let's just say for the sake of example that our second node was 10 here. Okay, so now we're trying to get to 1 below the answer. We're trying to get A here and B here. Because the issue is, if we get to a location where the nodes are meeting, then we could pass our LCA. We don't want to pass our LCA. We want to go to 1 below our LCA. So if they're the same, then we do nothing. However, if they're different, then we say A equals, then we move up. Ancestor AK and B equals ancestor BK. And at the end, the LCA equals to the parent of A, which of course you can also find in ancestor A0. Okay, this is it for LCA. Oh yeah, and the runtime of this is log n, because this first segment here, you do 20, which is log n, and the second segment here we are also looping through 20, which is log n. Okay, if you have any questions, continue to ask. For right now, I'm going to move on to segment tree, which is the second part of heavy light decomposition. Now, you could use a fragment tree, for some of it, but I'm going to go over how to use a segment tree. So I think the gold problem that sparked this video needed to use XOR. You can use XOR, you can use min, max, plus. For the sake of this video, I'm going to use min or max because that's something you specifically need a segment tree for and you cannot do with a fragment tree. And you can do fragment tree and do plus. You probably can modify it to do XOR too. Okay, so we're going to do a segment tree minimum query. So let's just say you have an array like this. Oh, I'm missing 3. Okay, and you don't have to have all the values, of course. This is just an example. Okay, so the type of queries you do is you're given like a range like this, and you want to find the minimum element in it in log n. And you also might have to do updates. You might say, okay, update all of these elements to be 1, or add 1 to all of these elements, or subtract 1. Those are the kind of different updates that you can do. Okay, so what a segment tree is going to do is, it's going to say, okay, each one of these is a node. Right, and what this node represents is if you are querying only this range, then 4 is your minimum. And the same thing for all the other nodes, like this range, 5 is your minimum. Of course, because it's just one element. And then you're going to make nodes of size 2. And the minimum here is 1, minimum here is 2, 5, and 3. And then you're going to make nodes of size 4. And then you make your big node a size 8. Now, I'm using this as an example with size of power of 2, but it would work just as fine if the power wasn't 2. Like, for example, if you had like 2 more here, put them 1 as 1, then you just put 1, and then you'll just have a smaller segment on the side. The code's not tricky at all to implement for that. It's tricky for segmentary, but not if the power is not if the size of the array is not a power of 2, it's not any trickier than the size of the array is a power of 2. Okay, so now let's just say I want to query the minimum of the range from here to here, right? Then I just look at these 2 blocks here, and I'm done. Okay, now if I want to query, let's say a little trickier range, let's just say I want to query from here to here. Then I look at this box here, and this box here. I take the minimum of those 3 and I'm done. So the idea is, what you can do is, you can, so I want to do this range, right? So I start with this big range here. I say it's too big. So I split up into its 2 sub-ranges. This right range here, it's completely within the range. So I say the right range is good. But the left range is again too big. So I split it here and here. This 2 here, that's good. It's completely within the range. But this range is too big. So I split it again. And this one is good. And the 8 I just dropped. So the idea is there are log n levels, right? On each level, I will look at a maximum of 4 elements. 2 elements on the left of the tree, like I did here, and maximum of 2 elements on the right of the tree. So this means that we're only looking for log n. We're looking at log n items maximum to do this. Okay, so how can we implement this? Where are the missing weeks? I want to watch them. Week 8 is probably not going to be public. Sorry. But week 6, all the rest of the week should be up. Okay, do I need to go over the code for segmentary, or should I just get into heavy light decomposition? I want to make sure no one gets like lost because they don't know segment trees, but at the same time, it's just a stepping stone to get to HDL or HLD. So yeah, okay, good for segmentary. Cool. So we can implement this. We can implement this by. So what we'll do is we'll give each of these nodes an index and an array. So this index will be 1, right? Then its left index will be 2 times what it is, and its right index is 2 plus 1. And the left index of here is 2 times of that, which is 4, and the right index is 2 plus 1. Then 2 times of this is 8, so this is 8, and this would be 9. And then the left index is twice of that, so that is 10, and that's 11. And then this would be 6 and 7, because it's 2 times 3, and 2 times 3 plus 1. And then twice of 6 is 12, plus 1 is 13, and here 14, because twice of that, and 15. And it turns out that even if it's not a power of 2, the maximum number of elements in the array would be 4n. So your array can just be of size 4n, and that would work. Okay, so to build your segment tree, actually, we can just assume that you actually don't need to build it. You can just also write the update function, and you can just go in and update all the values. Okay, so you're gonna do this recursively. So you're gonna start out with this here, I'm just going to recurse into the tree. So we'll call the function update. We'll say 1 because we're starting at index 1, and this represents the part of the array that goes from 1 to n, the whole entire array. And then we are trying to, and I'm just going to go over how to update one element. If you want to update more elements, you have to use something called lazy propagation. But that's fine. So let's just say this is the element that we're trying to, or let's just put this at location x, and we're trying to change it to val. Okay, so what our update function looks like is we have our index, we have the left of the array, we have the right of the array, we have the element that we're trying to update, and we have the value that we're updating it to. Okay, the first thing we have to do is we have to check if we are currently in the right range. So if x is less than the left part of the array, or it's greater than the right part of the array, then just return, because we are not in the range. Okay, now if we are in the range and we're at the exact value that we're trying to update, then we will just say, and this occurs if x equals r, if r equals l. So if it's in the range and the range is only one value, then we got the right value. So then we just say tree of our index equals to the val, or plus equals, depending on what your update function is supposed to do. Okay, and then we return, because then we're done. Otherwise, we have to update our two children. The first is at index times 2, and it represents the range from L to L plus R over 2, and x and val are the same. And we have to update our right child. That is index times 2 plus 1, L plus R over 2 plus 1. We don't want to overlap in the value. The right is the same. Okay. So we update our two children, and then we say tree index, and if we're trying to take a min tree, we'll say equals the minimum of our two childs. You missed you missed LCA, and then we're pretty much almost done with segment tree. We're in the middle of segment tree actually. You could probably just rewind and look at it, or you could keep going. Okay, what do you need? Min of tree index and val. I'm assuming you mean here? Oh, okay, you got it. Cool. Okay, this is the update function. Another function is we need a query function. Now, query we can do for a whole entire range, as I showed earlier. We don't need to limit it to, we just do that range. We don't need to limit it to one value. Of course, for updates we can do more than one value. It just requires something called lazy propagation. You can look that up. Yeah, if there's enough people who want it, I might do it next video, but for right now we'll just not. Okay, so when we call query, right, we still start with the index 1 that goes from 1 to n, and let's just say we're trying to query from the left location to the right location. Okay, so now we'll say int query. We have our index, we have our left, we have our right, we have our queried left, and original right. Okay, so the first thing we do again is we check if we are in the range. So this means that if original right is less than the left side of a range, or if right is less than the original left, then we just return infinity. Oops. We return infinity because we're doing a min query, we don't want to count this one. Okay, lazy prop. Keep that in mind. Okay, the next thing you want to do is if you want to see if we're completely in the range. right? Like when we're querying this range here, from here to here, we start here. Then this is, you go to here. Once 3 is completely in the range, we want to stop recursing there. We're just done with that. So if we're completely in the range, that'll be if OL is less than or equal to L, and R is less than or equal to OR, then we return tree of index. Because we already have the minimum of everything on our current range. Okay, the last query is that it's sort of like when we started here, right? From the 1, we recursed into our 2 subtrees. And you want to do that. So here we'll say return the minimum of query the left subtree, which is index times 2, L plus R over 2. Of course, OL and OR stay the same. And query of the right subtree, which is index times 2 plus 1, L plus R over 2 plus 1, and R, and then OL, OR. So we return the middle of those two, and that's our query function. Hi, is it Karthik? Hello, how are you? Okay, that's it for segment trees. If you have any questions, of course, you can keep watching. So now we're going to get into heavy light decomposition. Okay, I'm just going to copy the tree for here, for heavy light, just because I don't want to draw a new tree. Oh, cool. Okay, so for heavy light, we don't care. Glad you like this video. Cool. So for heavy light, we don't care about the depths of any of the nodes. All we do care about is the size of the nodes underneath them. Sorry, size of the subtree underneath them. So for all of these ones, the leaves are obviously of size 1. Should be of size 3 because there's 3 nodes underneath it. 2, 3, 4, this should be 5, and this should be 13. Okay, so now we have the size of the nodes on underneath us. So the idea of heavy light decomposition is that if you're trying to do like a query, like let's say one that goes from 4 to 9, like this, right? The first thing we do is we split it up at the LCA into a left path and a right path, or not only left or right, just like 2 paths that are just either going just up or just down. Like we don't want to go up and down. And then the next thing we do is on these paths, we make each path into some number of segment trees. And the idea is that we can put a maximum of log n segment trees on any path, so that you can you can traverse the path, and there'll be log n segment trees. Each takes log n to query, so it's log n squared to query a path in a tree. Okay, so what we're going to do is we're going to make heavy edges and light edges. So a heavy edge is going to be an edge that goes from a node to to its child node, which has the biggest size. And I'm going to mark heavy edges green. So from 13, the biggest node is 5, so that's an heavy edge. Now from 5, the biggest node is 3, so we continue the heavy edge. From 3, they're both equal, so we just pick any random one. Okay, now from every node that goes into the heavy edge, for all the other edges that are coming out of any node in the path that are not the heavy edge, we make them light. So we make all these edges here light edges. And then we repeat the process. So from 3, biggest one is 2, the biggest one is 1 here. There's no other edges to mark. From 4, the biggest one is 3, and there's only 1 edge. So we just mark that. And then there's 1 edge coming out of it. So we make this a light edge. Alright, so what does these heavy and light edges mean? So every color path you see here is going to be a segment tree. This means that in this green path you see here, you're going to build a segment tree on all of these edges. And then I suppose you don't need a segment tree for just one edge, but if you do put a segment tree, it'll just increase the runtime by a constant factor, so it won't hurt the runtime that much, and it'll be easier to implement. Okay, so that's a seg tree, this is a seg tree, seg tree, seg tree. This is a seg tree, and another seg tree. Right? All these edges are seg trees. So now, if we're looking at the path, let's just say from node 5 to node 12 here, right? We figure out the LCA is 1. So then what we do is we query this seg tree here, then we query this segment of this seg tree, and then we query this seg tree. When we query this seg tree, we query this segment of this seg tree. So through that, we can get all the edges on the path that we need, and we get them exactly once. Okay, so the question is, I've told you that there's a maximum of log n edges on a path from a root to a node, from an LCA to a node, but how do we prove this? Alright, so from any node, we always take the path, we always make it a heavy edge if it has the majority of the nodes in the path. So basically, this means that the maximum number of nodes remaining in any other subtree is n over 2. Yeah, this is complicated for a gold topic. There apparently was another solution where you could just use a 1D segment tree. But the idea is if you understand heavy light decomposition and you can code it up, then you can just use your template during the contest. Of course, if it's allowed. I'm under the impression that it's allowed, but I've heard people say otherwise. You might want to look into that. But you can just use your template during the contest, and then it takes you 20 minutes to AC it because you just use your template. Okay. So now we have right. So I was proving why there's only log n. Okay. So this means that in any for every light edge that we take, like this is a light edge, right? The red ones are light, the green ones are heavy. For every light edge that we take, its subtree has a maximum of n over 2 nodes in it. And the reasoning, of course, is that if there was more than half, then it would be the biggest subtree, and we would just take it with a heavy edge. Okay, so basically this means that we take a maximum, so two heavy edges are never connected together, right? They're always connected by a light edge. So if we can prove that we take a maximum of log n light edges, then we prove that the maximum edges is order O of log n, which is basically maximum 2 times log n, because we double it for the heavy edges. Okay, so we take a light edge. When we take the light edge like this one that we just took, the maximum nodes inside it is less than or equal to n over 2. And then if we take another light edge, then we have less than or equal to n over 4. And it keeps reducing by powers of 2 over and over again. And that is why the the number of light edges we take is a maximum of log n. Okay. It seems we have some extra time. I mean, I suppose I could end the video early, unless there are. Yeah, I'm gonna ask for questions. If there's no questions, do you have any resources to help reinforce understanding? Geeks for Geeks is pretty good. Geeks for Geeks has good resources. Yeah, I learned HDL through or HLD through Geeks for Geeks. Okay, I mean we're really early. Like this is less than half the time the class was supposed to be. I guess if there's no questions. Okay, so the main use for HLD is if you want to query something on a path. So let's just say that each edge in the path has a certain weight on it. So this could be like 5, this could be 4, 10, 2, 9. And if you're trying to query, say, the minimum edge weight on any path in the tree. Yeah, so it's basically used for a range query, the exact same range queries, but on edges in a tree instead of an array. You could probably modify it to be done for nodes on a tree too. So you could do min-max query, you could do XOR, as there was in that gold problem. Yeah. Okay, I suppose if there's no other questions, I would code this, but it is very hard to code right the first time. So we just want to use a template, and Geeks for Geeks has good implementation. I suppose I could talk a little bit about the implementation's details. So for each tree, you don't need to store whether it's heavy or light. That's irrelevant to the segment tree. All you need to do is store. Okay, so for each edge, you need to store which segment tree it's in and its index in that segment tree. You also need to store the segment tree, the index of the last element in it, and the segment tree that's on top. So for this edge here, you need to store that this is the next segment tree on top. Anyways, I'm glad you liked the stream. If you liked it, give it a thumbs up. Be sure to subscribe. And I will see you all next week for the final one.